So Yorgos, let's start the talk. So today we have Schödel.
So here I am. Okay. So I can just use my hands basically now.
Yes.
So what has been done in the Galactic Center is you take images with incredibly high angular resolution. Basically, you need to be able to take an image in the infrared where you can read the newspaper from from a kilometer distance, basically. No, I forget. Okay, I forget it. It's 100 kilometers distance, basically, where you can read the newspaper. And then you take these images every year. And then you compare what happens. One of the big problems is that there is no ruler in space and everything moves and you don't have a clean laboratory. So one of the big problems was to know if you look at if something has moved, is this just because your telescope has moved or is it because something really in space has moved? Fortunately, everything moves pretty much random, the stars, so you can assume that on average nothing moves, and then you can use this average to precisely align your images, and then you see that the closer you are to where you think the black hole is, the faster the stars actually are moving. You can actually, when you compare one image from one year to an image to the next year, you can see that stars move a tiny little bit, and when you're close to where you think the black hole is, they move actually by several pixels, which is quite a lot for something that is 26,000 light years away.
Just right, you should stress that stars are not supposed to do that because physicists sometimes don't realize about that, but the stars don't move, at least not in a human lifetime. And
well,
saying is that, well, yes, they move a little bit.
Well, when I walked into Reinhard Genze's office in the year 2000, and he talked me about measuring stellar proper motions, I also said, but stars don't move. I made a fool of myself because I had been doing this for years, and actually stellar proper motions have been even measured for about 100 years or so. So nearby stars move actually very fast, by a few arc seconds per year. So that can be done by taking photographs. That was even done with photographic plates from the ground. But I also have to say, I always thought it's just fixed stars. So I made a bit of a fool of myself. But he did not chop off my head. And and then I was taught the technique. And so we were measuring this. And all we were seeing stars moving in straight lines, very fast, with up to 1,000 kilometers per second, which is an incredible velocity if you think these things are stars of 10 or 15 times the mass of the sun. Now, the next step was in the year, and there was always a bit of a race because there was always a competition between the German group and the American group. And there was always the big thing, who comes first, who does things first. Nowadays, I find the notion of who does things first a bit irrelevant because in anything that is worthwhile in science is basically always done by several groups. And if only one person or one group is able to do something and it's not reproduced by another group, then it basically doesn't serve a lot anyway, because it's all about reproducibility in experimental science. And also, I mean, basically almost all big discoveries are being done at the same time at different places by different groups within 1 or a few years. So that is really not relevant whether somebody has come 6 months earlier or not. It's not sports, it's science. So the next step was then in the year 2000, for the first stars, we could measure accelerations. So you could actually see that they were not moving on straight lines, but on slightly curved lines. And once you measure the acceleration of stuff that moves, you can actually pinpoint the location of this acceleration. And it was pointing towards Sagittarius A star, which you do not see in the infrared images. It's dark. So this was another problem. If you have an image, where is your black hole? If you discover the black hole in radio and you make an infrared image, how do you know where your black hole is on the infrared image? And there, fortunately, there's stars that are bright in radio, so-called maser stars. And the black hole, or the supposed black hole, is also bright in radio, and you can measure accurately the distance. And by knowing the position of the black hole with respect to the stars in radio, you can also find it where it is in infrared images. And the acceleration of 3 stars was pointing towards this Sagittarius A star source. And statistical measurements indicated from the velocity dispersion that there must be something a few million solar masses heavy. Now, the exciting thing happened in the year 2002. When we went in Chile, we were observing. We were actually using for the first time the new camera at the 8-meter telescope. Before we were at the smaller 3.5-meter telescope. And then we realized that one of the stars was not at all where it was supposed to be, because we were just extrapolating where it has been going. But instead of being down here, it was up here. And a colleague of mine, Thomas Otti, immediately realized that this meant it has gone around the black hole, that it had actually swung through pericenter of its orbit. And then basically it was just a question of finding the right, or programming the right software and fit a Kepler orbit to the measurements. And then you saw that this one star was on an orbit of about 16 years period, which is not much at all, which is fortunate. That means we can do it in a human lifetime, this experiment, actually several times in a human lifetime. And the focus of this orbit is again the radio position of Sagittarius A star. The star passes within just 17 light hours of Sagittarius A star. 17 light hours is about 3 times the distance from Sun to Neptune. That is an incredibly small volume astrophysically. And from the Kepler solution of this orbit, we also know that about 4 million solar masses have to be inside this volume. And that it's very hard to come up with something that is not a black hole, that is so compact and that is also dark. Basically, there were some, of course, you can always come up with crazy hypotheses. There was the so-called neutrino ball idea that you have degenerate neutrinos, fermions, that can form a fairly compact object without being a black hole. But that would be too big for this stellar. That could already be excluded. And if you do something, there's some other ideas like boson, compact boson condensates. The problem is, if you have this over the lifetime of the galaxy, this thing accretes more and more matter, and it must either shine light because it accretes the matter, or it must collapse eventually. So that is the main arguments why we really think it must be a black hole. And we also know that black holes are astrophysically, or whatever, things that are extremely similar to black holes are observed astrophysically. They're everywhere. All the pieces of the puzzle, from all observations, from the kinematics, from the stellar orbit, from X-ray observations, from radio observations, from size measurements of Sagittarius A star, from the motion of the source Sagittarius A star relative to the surrounding stars, which can be calculated like Brownian motion, is a classical physical problem. Brownian motion, like a piece of pollen being juggled around by water molecules under the microscope. That's very, very similar. And again, this shows you that Sag A star must have a minimum mass of a few 100,000 solar masses, enclosed in a volume that is smaller than the Earth's orbit if you use the radio astronomy information. So if you plug all of this together, it is really, you cannot come up with a reasonable explanation that it's anything else but a supermassive black hole. And this is basically what the Nobel Prize for Physics was awarded for. And then, of course, these groups went on. And of course, just having a supermassive black hole there and saying that, okay, with all probable evidence in the world, it is one, that's already nice. But the next thing is, can you actually do some states? Can you actually measure something or say something about general relativity? Because in the end, the black hole in itself is already a quite interesting thing, but it's even more interesting because black holes are basically where quantum theory and general relativity collide, and where you have a contradiction in modern physics. And this is why they are so incredibly interesting, because in the end, physicists or any scientist always want to find something where what we think is true is not supported by evidence anymore, because only if you can actually show that some of our theories, ideas do not work, then we make actually progress, because then we have to think up of new things. So now the teams that are working on this, they have now dozens of orbits measured. So Reinhard's group and Andreas' groups, they have now several tens of stars with their orbits measured. We know at least 3 stars. Actually, there's another player yet, they're always being forgotten, but there's Andreas Eckert's group in Cologne in Germany. They're another German group that work independently. They also found recently a star that moves just in 10 years around the black hole. So you have now several stars that do this in a short lifetime, that you can actually follow this experiment in a lifetime. And now you can see whether these orbits that you observe actually do what, not just what Kepler predicts, but what Einstein predicts. So Einstein predicts that you have, that the redshift of the stars are different, that there's actually, for example, this one star that is still the best measured star, the first one with the orbit, has, it moves at a few thousand kilometers per second when it's close to the black hole, and it's very deep. It's about 100 Schwarzschild radii from the black hole. So it suffers the radiation, the light from the surface of these stars is redshifted due to special relativity. That's the time delay because of its speed, basically, of its transversal motion, and because of general relativity because it's deep inside a gravitational potential. And it's redshifted by about 200 kilometers per second, the light from the surface of this star, which is a lot, but due to many astronomical problems, it was a very hard measurement to do. And so when the star first passed through pericenter, so to the closest point of the black hole, that was in 2002, and then basically for 16 years, the 2 groups at Max Planck Institute and at UCLA were preparing for when the star would come back, to beat down all the systematic measurements, because all of this, I mean, it may sound boring if you're a theoretical physicist, but basically here the experimental part is, you're in nature, and nature is an incredibly bad laboratory because you cannot control anything, and you're full of systematic errors. And basically 16 long years, dozens of people have basically taken a club and beat down on the systematic uncertainties and errors and improved the instrumentation. And then actually they were able to show a few years ago that indeed the light of the star is redshifted exactly as predicted by general relativity. Now Reinhard's group have gone even further. They have, together with dozens of other institutes in Europe, constructed a big interferometric instrument. So they combine now several of these 8-meter telescopes in Chile, and they get the angular resolution of a 100-meter telescope now. And they even claim now that they see the deviation of the orbit from a classical ellipse, because what general relativity tells you is that you have a Rosetta-shaped orbit. The orbit does not close anymore, but it precesses. This can be due to general relativity, or also because you have some extended mass around the black hole. And all these measurements have been done. They have worked. They are incredibly powerful. And this is basically where we are right now. So this is what's going on with the massive black hole at the center of the Milky Way. And I will not bother much more you with my talk, so maybe it's better if we go over to questions to be more interactive. Just one word about my own research. So I'm still involved with the UCLA group now a bit with these stellar orbits. I mostly do image processing. But I have now taken a step back. I look at now the larger environment of the galactic center, the nuclear star cluster, and what else is happening there, and about how massive stars move and form around the environment of the black hole. Basically, my argument is, if you study an elephant, in order to understand the elephant, you also have to understand the ecosystem it is living in. You cannot understand such a star in isolation. And for example, with my group, we have shown that 80 or 90% all the stars around the black hole, they're all very, very old, 8 to 10 billion years old. And basically stars, in order to form stars at the galactic center, you need gas accreting to the galactic center. And in order for a black hole to grow, you also need gas. And the stars, you don't know the history of the black hole, but the stars can kind of give you an idea of the accretion history of the galactic center. They are kind of a fossil record of the gas that has fallen in there, because some got accreted into the black hole and some of it formed stars. And so we know that The black hole probably gained almost all of its mass very early in the universe, so maybe 10 billion years ago. Okay, I will stop here. I think without any pictures, it may make more sense to do some more interactive questions.
It's people, they must have
If
some
you have not
questions.
fallen asleep yet.
No, they have not.
Hope not.
I would like, if possible, to have an idea of what percentage roughly is the mass of the black hole with respect to our galaxy. 0.01%?
Much less. So it's, I think, so in typical galaxies, the black hole, so in a typical galaxy, in a spheroidal galaxy, the black hole has, I think, like something 0.01% of the mass, but in our galaxy, it's a bit less. So our galaxy, so if you take the total mass of the galaxy, if you include dark matter, I think our galaxy is roughly 10 to the 12 solar masses, while the black hole is something like 10 to the 6 solar masses. So this is nothing compared to the mass of the galaxy, if you just talk orders of magnitude. If you talk normal matter, it's 10 to the 11, the entire galaxy, so including the halo and everything. If you just take the galactic center, so there's the galactic center is dominated by a 200 parsec structure that is the nuclear stellar disk, that has 1 billion solar masses, while the black hole has a bit more, it has a few million solar masses, so there you're in a factor 1000. So basically for the dynamics of the entire galaxy, the black hole is not important at all.
Yeah. So I think instead I wanted to ask something. You just talk, people, don't raise your hand.
Talk anything that comes to your minds. I mean,
what is the three problems you mentioned before? Three problems. Can you hear me?
Yes, I hear you. But what problems I mentioned compared to physics, to measurements?
Yes. I just hear there are three problems, and I haven't understood them.
But problems related to the center of the galaxy, to the black hole, or to observational methods?
Probably the last one.
Probably
just which 3 points?
So in the observation, the problem is you need high angular resolution, you need infrared in order to overcome the high angular resolution, infrared because of extinction, and the next biggest problem is how you align your images with respect to each other from young year to the rest. Basically take into account image distortion, take into account that everything moves in there, because you do not have a clean laboratory. It's very hard to measure the positions of stars with respect to nothing, basically, because you do not have a ruler in space. So maybe these are the three problems that you were referring to.
Yes. I think Cuba wanted to ask something, but they just went silent.
I have a question.
Go ahead.
Okay, so why is there a reason of why will there in the middle of the Milky Way of the galaxy there will be a black hole? Is there a very important reason why would it be there? I mean, is there any reason?
Excellent question, actually. Okay, first of all, if we are guided by evidence, we basically see that the black holes are always at the center of galaxies. If they were not, they would actually, if they were somewhere else in the galaxy, they would suffer an effect that is called dynamical friction. How can probably explain that very well to you. It's if you move a heavy object through a sea of stars, it will always have a higher concentration of mass behind its path, because it's like a gravitational focusing, and it will be slowed down. So it will always sink very quickly to the center of the stellar distribution. So whenever you have something, a massive particle like a stellar black hole or a massive black hole or an intermediate mass black hole, it will sink to the center of the stellar system. Except, and that is in later talks, I think you will talk about gravitational waves and merging black holes. Black hole mergers can actually kick a black hole out of the galaxy because you get, and I am out of my own depth here because this is not my field, because if you have asymmetric radiation of the gravitational waves, you have a recoil, and that ejects, you can eject a black hole from the galaxy. But usually heavy particles always sink to the center. And the other thing is the black holes in the past were growing. You observe that in observation. When you look at back past of the cosmos, you see quasars, you see very active galactic nuclei, and you see how black holes actually devour large amounts of matter, about a solar mass per year. So they quickly gain huge amounts of masses. And of course, you can only grow when you are at the center of a galaxy. You can grow big and fat because you're at the center of the gravitational potential where all the gas is falling in.
So if I understood, is there a chance that the black hole was prior to the matter that is around it in that place?
Yes, there's a chicken and egg problem, but it's true that it's possible that at least the black holes were kind of there. Well, probably the black holes were there very early, and the galaxies grow around the black holes. And yes. So, or as we said before, the mass of the black hole now is nothing compared to the mass of the galaxy. But if you go back into the past, very far back in the past, the black hole maybe have been the condensation point of the galaxy.
And another question I have was, you were talking about these nuclear clusters, and how is the angular distribution of this matter around the center of the galaxy? Is it isotropic distribution, these nuclear clusters?
No, the nucleus clusters rotate as the Milky Way. They are slightly flattened. They're not exactly isotropic. They are rotating. They're close to spherical. They kind of has an isotropic velocity dispersion, but they rotate. They're slightly flattened. And if you go outside of the nuclear cluster, then there's a very flat rotating disk around the black hole on larger. But that's only the case for our Milky Way. In other galaxies, if you have spheroidal galaxies, you can have a completely different kinematical distribution of the stars around the black hole. So that's very specific. That really depends on the kind of galaxy you look at.
Okay, thank you.
You're welcome.
Somebody else? There are two shapes.
So,
Hi, Professor Reiner.
Hi.
Can you hear me?
Yes.
Yes.
Very well.
Okay, I have a question for you. What is the relation between the massive of the black hole and its size? I mean, when you have a supermassive black hole, it means that you are going to have a large black hole in dimension, I mean.
Yeah, well, astrophysically speaking, a black hole is always incredibly small. So, for example, the so-called, basically the black hole size, let's say the black hole size is the same as the Schwarzschild radius. And the Schwarzschild radius for one solar mass, so if you could make a black hole out of our sun, then the Schwarzschild radius would be 3 kilometers. And the black hole at the center of the galaxy has 4 million solar masses, so you have 12 million kilometers of Schwarzschild radius. This is still very small. This is still inside the orbit of Mercury. And astrophysically, it's very small. This is also why it doesn't really accrete stars or so, because it's just an incredibly small point in space, and stars are also points, and space is incredibly big, and the stuff just flies around, and only maybe every 10,000 years or so, maybe a star hits a black hole in the center of a Milky Way.
Okay, I had this question because in a lecture yesterday, it was shown to us a simulation of two black holes, and they were moving around, and they had the final unique black hole. But this final black hole was larger than the initial black hole. And so I thought if you have more massive, you are going to have more gravitational force on itself. And I thought you are going to have a smaller black hole instead of a bigger black hole.
No, the concept of size, I mean, if you think in general relativity, the black hole is always a singularity, no matter what its mass. The only thing that changes is the event horizon. The event horizon, in my very poor understanding of general relativity, I just talk in very basic terms here, is basically where the escape speed is the speed of light. And that just grows linearly. The size of the event horizon just grows linearly with the mass of the black hole. So you can directly take 3 kilometers and multiply it with solar masses, and then you have the size of the event horizon.
Okay.
The gravitational has energy of always 3% of the total mass. You mean? Do you mean that?
Are you asking me or the other speaker?
Yes. I hear you're talking about gravitational wave by binary, and is there always 3% of the total mass converted into gravitational wave?
So a little bit of context here, Rainer, because yesterday we had Leo Baraka talking about the semi-structural spirals, and the question that you're asking, Chan Jiayi, is that about 5% of the mass is converted into radiation, but that's very unlikely to happen at the Galactic Center because, as I was explaining yesterday, you have to wait about 100,000 years to see one of these, right?
Yes.
So taking into account that we live, 80, 90, in my case, maybe 120 years, if you divide 120 by 100,000, the probability is very, very small. So it's very unlikely that we will ever see this happening at the Galactic Center. So it's like a non-existent for all kind of pragmatic purposes.
So I just hear you that there are 1,000 years and 5% total mass and.
Yes. So the point is that this is you have one of these every 10 to the 5 years, and if you live 80 years, the chance that you get one of these during your lifetime is very small. You're not going to see them, right? So, but in any case, when you have two merging black holes, the energy radiated is of about, this is a lie, but anyway, it's of about 5% of the mass is converted into pure energy. It's like converting mass, that E equals mc squared. So you're translating that mass into pure energy, which is why these gravitational wave events are so powerful. But in particular in power output, because, for instance, the first event detected by LIGO had a total power output of something like 40 times all of the stars in the whole universe. Because we're talking about power output, you're divided by milliseconds. If you talk about the energy only, in quotation marks, you are annihilating, like, I think in the case of the first gravitational wave detected, it was something like 5 solar masses. So you are putting 5 suns entirely, their masses, into energy, and that's a lot, right? It's something like 10 to the 54 ergs, if I am not wrong now, which is a lot of energy.
54 ergs.
Yes, if I'm not wrong. I just made a calculation of that with my head.
Yeah, I don't know, Eric. What is ergs?
Well, you can also talk about watts if you want, but this is just a trivial calculation. We can maybe talk about this later, if you're fine with that. So Cuba, people, do you have more questions? Because this is for you.
Yes, I would like to make a question.
Go ahead.
Professor Schödel,
Yes,
can you hear me?
Rainer.
yes, very well.
If I understood well, you said that the black hole in the center of our galaxy is like the condensation point of the galaxy itself. Uh, I was wondering if there is another, if it is necessary for to the formation of a galaxy to have a black hole in its center. Isn't there another galaxy formation model in which a black hole isn't involved in its formation?
Well, we do know, no, not necessarily. So we do know observationally there's small galaxies. So all big galaxies like the Milky Way, they have a black hole. There's just no exact.
Yes.
But there's small galaxies that do not have a black hole. So basically, where observation tells you there's nothing.
So you have found, I mean, the astronomic community, galaxies where they don't black holes in its center.
Yes. So basically, you caught me there. So it's wrong what I said. So they're not the condensation points of galaxies because obviously you can form galaxies without black holes.
Yes.
What you need is dark matter halos. Once you have some kind of seed black hole of a few hundred solar masses or so, it will sink to the center and accrete matter there. But basically, it's still a bit not clear how galaxies evolve and form. So whether there's just small galaxies and then they merge together, or whether you get these big, and that's actually been a surprise in the last years of observing very, very high redshifts in a very early universe. One can find already very big galaxies with very big black holes. But there are also the small galaxies where we really, to the best of our measurement, do not see anything. For example, the Magellanic Cloud, the Large Magellanic Cloud, there's no evidence at all for a black hole at its poorly defined center.
I have a question there.
Go ahead.
Is there a chance, taking into account all the things you just said, that at some point what you need, you probably need is a gravitational center on a galaxy, right? Every galaxy should have one, maybe a black hole if you're a big one, or something else if you're a small one. But at some point, is there a known or a prediction of distribution of black holes in the, let's say, in a significant area of the universe, so you can predict how will galaxies form depending on the distribution of black holes and big mass objects?
No, not really, because basically you only observe the black holes when they're inside galaxies. If there were a supermassive black hole outside of galaxies, there could be. I mean, we would see them by gravitational lensing, but just to mention, there's lots of them outside of galaxies. We could not know of their existence. We cannot observe them.
And there's no way to predict their creation after Big Bang.
There are people who work on that, who actually try to. So there's some people who favor that at least part of what dark matter is primordial stellar black holes, but you cannot form massive black holes in the Big Bang. I think a lot of the observational space has already been excluded, but you could have, for example, solar mass black holes from the Big Bang that are remnants. You could have that, but that again is something that is very hard to show observationally. The problem is a black hole is something very hard to see.
Okay, and if you have a black hole, what are the chances that, I mean, independent of matter and the mass it contains, how long would it take to create a galaxy around him?
That's a very good question.
Yeah. How long would it take? I don't think if you could play God and take a black hole and put it somewhere in space nowadays, you would not form a galaxy around it, because that only worked at the beginning of the universe when the gas was dense enough in the universe together so it could collapse. So basically the structures, so you do not find basically, you only find the massive black holes at, I don't know, have you ever seen these images of what the cosmos looks like on large scales from simulations or from observations? It's like a sponge, basically. You have huge areas of nothing, and then the matter, which is the galaxies, they are distributed in thin sheets and filaments, and then sometimes they cross, and at these nodes, you get the very massive galaxies and very massive black holes. But you do not, if you, for example, nowadays, so basically, you create galaxies and black holes where you have condensations of matter. First dark matter, and when the dark matter condenses, it always attracts the visible matter as well. But you would not expect to find black holes in isolation or for them to form in isolation. And if you could take a massive black hole and set it somewhere close to the Milky Way into the universe, it would not create a galaxy because there's not enough gas around in the modern universe to create a galaxy.
Sure,
Does this kind of answer your question?
Yes.
I have a question.
I think that Sultan Jaime is going to talk about this, but the summary is that what Ren was saying. So at the beginning, if you believe in dark matter, because you have to believe in it, right? So you have these deep potentials, and the baryons are, so all of the matter you have in the universe is like 20% of the matter is baryons. So they follow the poor baryons. The only thing that they can do is to follow the deep potential wells that this dark matter create, right? So at the bottom of that potential well, you would, accumulate gas, which would form proto-galaxies and would form, you would have probably a condensation of black holes there, which could merge with each other, etc., and grow over time. But there are many different scenarios, and while there is an emerging consensus about the creation of these supermassive black holes, there is still a lot of debate going on. But Sultan will talk a lot about this.
Okay, thank you.
I have a question.
Go ahead.
Hello, Professor. My name is Doris. I want to know if there is a future. What's the future of a black hole?
Thank you very much. I'm a poor observer, and I always feel like an imposter when I give answers to these questions, because I have to confess to very strong ignorance. So basically, what I know about these kind of questions, what I pick up from dumbed down articles in maybe magazines for scientists. But so the future of a black hole, I give you now what I know, and I invite every theoretical physicist here to protest strongly in case I say something stupid. Basically, general relativity says the black hole just grows and grows and grows when it can accrete matter, and if it doesn't accrete matter, it just sits around. Okay. Now, Stephen Hawking showed, I think already in the 70s or 80s, that if you take quantum physics into account, because the quantum vacuum basically has a high uncertainty. So basically, if you look at a vacuum, there's never nothing in quantum physics. There's always something. It's kind of bubbles. You have these virtual particles that pop into existence, particle, antiparticle, and pop out of existence again. And very close to the event horizon of the black hole, but if you just imagine it as an infinitely thin sheet, what can happen is that, and this is the part that I don't remember exactly, for some reason the antiparticles get accreted more, and then the black hole loses a bit of mass and radiates away a photon. And this is called Hawking radiation. It's incredibly cold, so you can translate that into a temperature, into a black body spectrum, and something like a black hole at the center of the galaxy would be colder than anything you could ever create on Earth. But the smaller the black hole is, the hotter it would become, and the faster it would evaporate and lose mass, until eventually it goes away in a big flash of gamma radiation. So thanks to Hawking, we believe to know that black holes actually evaporate. So if you wait for many orders of magnitudes, the lifetime of the universe, maybe all the black holes eventually will disappear.
Yes, but it's going to take a long time. If you consider a solar mass black hole, I think the time scale is something like 10 to the 64 years.
Yeah, so it's pretty long. So it's not just a few orders of magnitude. It's something mind-boggling.
We discussed a little bit about this yesterday with Neil Turok.
I have a related question here.
Yes.
So, what is the destiny of the galaxy? Eventually, the black hole at the center will eat all the matter, or this system is stable in some way?
Very nice question. Actually, very good question. In principle, it's a stable system. So of course, if you think about, as Pau just said, if you think about 10 to the 60 times the lifetime of the universe or so, that's different. But if you just think about now the Hubble time, basically the lifetime of the universe, the black hole at the center of the Milky Way right now is doing nothing. It's surrounded by stars, but the stars just orbit around it. And it just, at the moment, it maybe accretes 10 to the minus 8 or 10 to the minus 9 solar masses per year in mass. And it's again, the black hole is something incredibly small. There's lots of angular momentum. And if you cannot get rid of the angular momentum, nothing falls into the black hole. So if you just wait for a long time, all the massive stars in the galaxy die. And then at the end, you're just left with red dwarf stars that live for 100 billion years. And they just circle happily themselves and the galaxy and the black hole. But the black hole will not grow substantially more massive, except maybe in 300 million years when the Milky Way will collide with the Andromeda galaxy. Then we have something that is called a massive galaxy merger. And in these collisions, actually lots of gas is funneled towards the center, and then everything will be transformed. Our Milky Way and the Andromeda galaxy will be transformed. They will go under enormous starbursts. There will be nuclear activity, lots of gas into the galactic center. The black hole will grow crazily, and at the end we will have an elliptical galaxy with red stars, no star formation anymore, and a more massive black hole. But then things are getting boring again. Then nothing happens again.
The fun thing, that was a very, if I might be pedantic, Rainer, interrupt you again. This is a very interesting question because a black hole from the point of view of a galaxy, as Rainer was mentioning before, is tiny, it's ridiculous, it's nothing, it's microscopic. From a distance of about, say, 3 parsecs in our galactic center, if I'm not, I think that's correct, Rainer, does not feel the black hole at all, right? And a galaxy has 14 kiloparsecs of length, right? So it is, the strange thing is, how does the galaxy know that there is a black hole at the center? Because for some reason, the properties of the galaxy correlate with the properties of the black hole, and we do not understand why. But I am very, very sorry for doing this, but it is 7 here in Spain, in Central Europe as well. And I see Pablo Laguna in the public, and I guess that Pablo is waiting very patiently. And the problem, Pablo, is that we had some technical problems at the beginning, so we were a little bit delayed. But unless you have, say, 1-2 important urgent questions to write, and maybe we could stop now. I don't want to spoil the fun.
Professor, you said redshift predict by general relativity. What's that?
Was it me or Rainer?
Pardon?
Go ahead.
So
I mean, I hear that you said a redshift from general relativity. Just that.
The redshift, basically, it's a different way of saying that a clock goes slower. It's time dilation. And if you have a star, you can look at spectroscopically the star, and stars have emission lines, atomic or molecular emission lines. And these emission lines are frequencies. That's nothing else than a clock. And the clock goes slower when you're close to the black hole, and that means your emission line is red shifted. shifted towards the red, towards longer wavelengths. The red shift, that is an astronomical jargon, basically. It's an astronomical way of saying you are either flying away from us or you're deep in a gravitational potential, for example. Does that clear it up?
So this is from theoretical prediction, or we have observed that?
Yes, it's both theoretically predicted and observed. First predicted, and then 2 years ago observed.
So the clock exactly goes slowly nearby the black hole.
Yes. So when you look at this one star, which is called S2 or SO2, when you look at the spectral line on this star, the spectral line tells you basically how fast the clock on that the star is going. Now, if the star is deep in the potential of the black hole, the clocks are going slower and the line is redshifted. And there's also a second effect. The star is moving at a few thousand kilometers per second. That's 3% of the speed of light when it's close to the black hole. And that also, because of special relativity, that also tells you that we as an external observer should also see slower clocks. So both of these effects add up to a curiously redshift in exactly the same magnitude.
Yes, but you don't have to go to the Galactic Center for checking this. It's enough with your cell phone.
Okay, thank you very much, Professor.
You're very welcome.
I have a question.
Last one. Diana, go ahead.
Thank you. Would there be any consequence if in the stability of the galaxy if this black hole is not there? What is its role?
Okay, this is again one of the most fundamental questions I think that we have here. So first of all, and if you also listen to what Pau said before, we have, if you could magically make the black hole disappear, okay, some stuff would jiggle around in the middle, but where we are, or even at a few light years distance, at 10 light years distance from the black hole, you don't already feel the black hole because the gravitational mass of the black hole is nothing. However, curiously, we know that black holes somehow affect the formation of galaxies because it depends on this is a bit more astronomical detail, the bulge, the spheroidal part of the galaxies, and our galaxy doesn't really have that. They are very tightly related to the black hole mass. What happens out in the disk, that has nothing to do. So I tell you, okay, let's put it that way. If you can make the black hole disappear, really nothing would happen to our galaxy. However, if you go back in time and if you observe the cosmic history and the galaxies, only large galaxies that have spheroidal parts, only those galaxies, there the galaxy formation and the black hole existence are intimately connected, and we still do not know exactly how and why, because as Pau has underlined, the black hole is just so infinitely small and really doesn't have much mass compared to the rest of the galaxy. But there is an intimate connection that is still not understood.
Can I go pedantic again?
Yes, please.
Nice. So, Diana, so the point is that if you have, for instance, we know that black holes in principle should merge, supermassive black holes. If you have two supermassive black holes merging because of gravitational radiation, unless they have exactly the same mass, and if they have some spin, and those spins are not in a very peculiar configuration, when they merge, they will receive a kind of a kick. And that kick can be a kick velocity, or like a recoiling velocity. And that recoiling velocity can be as high as 4,000 kilometers a second, which means that in principle, you could have a galaxy with a binary of two supermassive black holes at the center of it. And those supermassive black holes, at the moment of after they merged, they would just disappear from the point of view of the galaxy, because they would be traveling. So the final system would be traveling at 4,000 kilometers a second. The escape velocity of the whole galaxy is much, much, much less than that. So from the point of view of the galaxy, the black hole, the end result that would be there, and a millisecond, in quotation marks, later, it would not be there anymore. From the point of view of the galaxy, nothing would happen. From the point of view of the galactic center, which was what René was talking about, it would take about. It depends on the mass of this nuclear star cluster, but it would take about a Hubble time for the system to recover a kind of thermodynamical equilibrium again. So actually nothing would happen, which is why all of these correlations that Rainer was talking about are so mysterious, because the galaxy is like it doesn't care, it doesn't actually, if you allow me, give a shit about the existence of the supersonic black hole. But yes, Rainer, this is a pity because people are excited, but on the other hand, we have Pablo waiting, and maybe if you are fine, we could stop here.
Yes, we can stop here. So thanks again for joining in, and my apologies that this has not worked as well as I thought, but maybe it was nicer that way. I don't know. I really enjoyed being with you all today. Thanks a lot, Pau, for setting this up, for making this happen. This is and Lionel, thank you very much. And yeah, if you have any more questions.
Another point not clear. I'm not clear that what is the second effect that verifies the redshift of stars. The first is you said nearby the black hole, and the second as you said 3% speed of light. What's that?
That's the velocity of the star when it flies by the black hole of the star S2.
Okay, now I really have to
Thank you very much.
Like a benevolent dictator and stop